All right, this is the last piece of our climatological puzzle, and it has to do with what happens when air masses with different characteristics interact. But first, before that, we have to look at what an air mass is and how it gets these characteristics to begin with. So this next little bit is about air masses. Each of those little bubbles on the projector over there symbolizes an air mass. An air mass is just a big body of air that has similar characteristics throughout it. And the characteristics I'm talking about are temperature and humidity. So, once again, every time I say air mass, what I'm talking about is a large body of air with similar characteristics throughout. Meaning everywhere in this big body of air, the temperature is about the same, the humidity is about the same. What determines the temperature and humidity of an air mass? Where it came from, where it was most recently. So as these big bubbles are sitting where they are, they're going to be not sitting stationary. Everything's slowly moving because of global convection and the Coriolis effect. But they're going to be assuming the characteristics, or assuming temperature and humidity due to the place where they are. So, say temp and humidity, because those are the characteristics we're concerned about, are a result of where the air mass, say, came from most recently. The characteristics of these air masses can change as they move. What you'll notice if you can read that picture from where you're sitting is that each one of these air masses is symbolized by two letters. It has, the first letter is lowercase, it's either an M or a C, and the second letter is uppercase, and it's either a T, a P, or an A. And those tell us about where the air mass came from and what characteristics it has. The first letter, the M or the C, tells us whether the air mass was sitting over land or whether it was sitting over water. The C means continental, and there are three of those. Continental, 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 means they were sitting over land. The M's, of which there are four, maritime, maritime, and the two over on the left side of the map, those mean maritime means it was sitting over water. And those influence the humidity. If an air mass is sitting over the water, there's a lot of potential for evaporation, and so those are going to be more humid air masses. The air masses sitting over land are the continental ones. There's going to be less potential for evaporation, so they're going to tend to be drier or less humid. So, let's see. Maritime air masses tend to be more humid because they sit over water and continental air masses are the opposite. So the first letter of that two-letter code is telling you whether it's continental or maritime, and that's going to tell you what the humidity. Incidentally, that also tells you what the pressure, because as you may remember, dry air masses tend to exert higher pressure because they're all heavy oxygen and nitrogen molecules, or mostly. The humid air masses tend to exert lower pressure because they have a higher percentage of those very light water molecules in there with the air molecules. The second letter tells you about the temperature of the air mass, and the temperature has to do with the latitude it came from. Down here we have big T, big T, big T. That stands for tropical. Those are going to be warm air masses. Big P, big P, big P, those are going to be colder because they are polar air masses. And big A, that one's going to be really cold because it's Arctic. So that's the second letter is telling you. So tropical air masses are warm, polar are cold, and Arctic are wicked cold. If you see a code, I'll write a little example out here what this is going to mean. Yes. Yeah. Let's say the first letter, that's maritime. That's continental. And that first letter, once again, is telling you maritime or continental. And this T would mean tropical. And this P would mean polar. So if I asked you what the pressure of these air masses, say, okay, tell me what the pressure of a maritime tropical air mass. You'd be like, well, warm and humid, both of those things are going to mean low pressure. Continental polar, you'd be like, well, dry and pretty cold. Both of those things are going to mean high pressure. High pressure, low pressure. If you ever hear about a high pressure system or a low pressure system, you're probably talking about an air mass that has some combination of characteristics that give it that high or that low pressure. All right, let's look at what happens when the different air masses bump into each other. Oh, actually, there's one more thing I want to write. Air masses move around the planet because of convection and the Coriolis effect. Was the thing I was going to mention. The last thing I was going to mention. So air masses move around the planet. Because of global convection and the Coriolis effect. And I guess you could also add where air masses meet, we get weather. You'll see what I mean by weather in just a bit. So air masses move around the planet because of global convection and the Coriolis effect. And where the air masses meet, we get weather. And weather usually, what we refer to as weather, like unusually dramatic changes or events, like a rainstorm, thunderstorm, tornado, that sort of thing. That is because because different air masses are interacting with each other at what is called a front. A front is just the border where two air masses are meeting. So front, it's the say border where two air masses with different characteristics, once again, I'm talking about temperature and humidity, are meeting. The front is the border where two air masses with different characteristics are meeting. You usually hear about cold fronts and warm fronts. Those are the most common kinds of fronts. There are other kinds of fronts also that I'm not going to bother talking about because we don't have that much time. It's sort of beyond the scope of this class. When there's a cold front and when there's a warm front, the only difference between the two is which air mass is moving into the other one. If the cold air mass is moving into the air mass, that's a cold front. If the warm air mass is moving into the cold air mass, that's a warm front. So it's really just which air mass is pushing into the other. That defines what kind of a front it is. So cold front is when the cold air mass is pushing into the warm one, and a warm front is vice versa. It sounds like the music from Jurassic Park.
Can you check if they're watching Jurassic Park?
No. All right, what happens when air masses with different characteristics meet? And that diagram I've got there on the projector is showing you a good representation. And the diagram that you're going to have to look at in your interview looks very similar to that. It's just a different version of the same thing, basically. Just the most important thing to understand about when two air masses with different characteristics meet, for example, if we have a cold air mass over here, and we have a warm air mass over here, the border between the two, don't draw this line, is not vertical. It does not look like that, where two air masses just sort of come and smush together. Because this one is colder than the other, which means what with regards to its density? If something is cold, it is dense or not dense? It is dense. The molecules are more tightly packed together. So, if you've got a more dense air mass and a less dense air mass, and you let them layer out, which one's going to end up on bottom, which one's going to end up on top? Think of anything we've done with density and stratification this year. Things that are dense end up where? On the bottom, like the cup with the syrup and so forth. And things that are less dense end up on the top. So what's going to happen when the cold air mass and the warm air mass meet, especially if the cold air mass is pushing into the warm air mass, it's going to wedge underneath it. And I used the expression, or used the example of a cow catcher on a train last class, but then no one had seen a cow catcher before, or knew what I was talking about. He just needs to get into Mr. Newell's room. He's 7-4 on the door block. So I will look up a picture of a cow catcher so you know what I'm talking about. I like the example. Okay, those are cow catchers, what you see on the front of a train.
Why is it called a cow?
Well, because in the early days in the United States, when there was lots of open grassland and the cattle herds wandered freely around, they often would wander across the train tracks. And if a train hit a cow, it would probably derail. And so they put those things on the front so that it would it would wedge underneath the cow and probably toss him off to the side so that it wouldn't derail the train. So those things on the front of trains are called cow catchers.
Or kill the cow, right?
Might, I don't know, it depends on how fast the train was going, I guess.
Wait, so what does it do?
Well, if there's a cow standing on the train tracks, the cow catcher can just sort of wedge underneath the cow's legs or body and then lift him up and push him to the side, rather than... I don't know if the cow would go flying, but if you like that visual, that's okay.
Can you look up a video of that?
No. What's that?
Right there.
What?
Oh, yeah. Yeah, so the cow catcher wedges underneath the cow and pushes the cow off to the side, hopefully. Instead of just running over the cow and then it derails the train. So anyway, the cold air mass is playing the part of our train with the cow catcher. As it comes pushing into the warm air mass, because it is more dense and wants to be underneath the less dense warm air, it actually will sort of wedge underneath the warm air like this. So that, you remember how I said the border was not vertical? It's not vertical because as the cold air mass pushes in, it will tend to wedge underneath the air mass, the warm air mass, because the warm air mass is less dense. What that means is that the warm air mass, as this comes smooshing through, the warm air mass is going to get pushed upward. Okay. What's going to happen to the temperature of that warm air mass as it gets pushed upward? It's going to get colder, so the temperature is going to go down, so relative humidity will go up. Relative humidity can get driven up very quickly, especially if this is a warm, humid air mass, and it gets pushed upward by a cold air mass that's coming through the area. Very, very rapidly, the relative humidity can get driven up past 100%, lots of condensation, big fat clouds forming very close or very low, and then you can get lots of heavy rain and sometimes thunder and that sort of thing. So, yesterday, you'll remember in the afternoon when it finally cleared up at about 5 or 6 in the afternoon, it was sunny and warm. It hit 70, I think. It might have even gone a little above that. But it was really humid. So we had a big, warm, humid air mass sitting over the city. And today, we've got a cold air mass pushing through the area. It's going to wedge that warm air mass upwards, cause really rapid cloud formation, and there was the potential of thunderstorms in the area. And that's why. Because when you get this really rapidly rising warm, humid air mass, you get very fast cloud formation, lots of friction between particles of water, and potentially you could get a thunderstorm. So, what should you know about that? Well, you should know this. Warm air can get wedged upwards by colder, denser air. And when warm air rapidly rises and cools, there is potential for clouds, rain, T-storms, etc. So when warm air rapidly rises and cools, there is the potential for clouds, rain, thunderstorms, etc. Part of that etc. is tornadoes and hail. This was actually a couple of summers ago. It was the summer before last, Father's Day. The Father's Day right after school let out, and there was a hailstorm on June 20th or so, and there were hailstones the size of quarters. Anybody remember that? 2 summers ago? It was like the weekend right after school let out, and it was warm air, and we had a thunderstorm and a hailstorm. There was hail the size of quarters on my back porch. I actually have pictures of it on my iTouch, but unfortunately they're not on my computer. Let me show you. Actually, you know what though? I might have a video. I'll check. So these are more like the size of the ones that fell that day, that Father's Day here in Maine. But some places they can get really, really big ones like that big, and they do things like that to your car, if you're not lucky. Those ones you can see are about the size of a baseball. That happens when there's a really violent updraft, and these small particles, you have this, you have these rising, cooling molecules, and when they condense, you can have more and more water depositing onto them as they rise upwards through the cloud, and then they ultimately can fall. This kind of hail is typical of this. You sort of see the same kind of weather patterns that create this kind of hail, create tornadoes. And if we go back to, let's see if I already closed it out. If we go back to this map again, maybe you'll get a better idea as to why we get that kind of weather in these parts of the country. Right here is where we get a lot of this severe tornadoes and hailstorms. And what you can see right here is this is right where the maritime tropical air masses moving up off the Gulf of Mexico are going to be meeting these continental polar air masses coming down out of Canada. And so you're going to have the potential when those air masses meet for a very violent version of this to be happening, and then so you can get big hailstones. And as I tried to explain to my previous class, there has to be special circumstances to get a tornado, which is like there has to be a rotating updraft called a mesocyclone, and meteorologists are not really clear on why you sometimes have them and why you don't, which is why you sometimes get tornado formation and when you and sometimes you don't. But that's why we're always chasing storms around, because we're trying to get a better idea of why tornadoes form. Did you rewind back then? And that's what happened yesterday out in Oklahoma, which is somewhere in this area, is you had a really serious version of this. Cold air mass wedging under a warm humid air mass, driving it up, cooling it off, and ultimately resulting in some serious tornadoes.